All right, thanks for that introduction. So I'm very excited today to be presenting this work, which is actually a couple of works that's submitted to a NeurIPS of this or of last year, uh, focusing on using diffusion models to solve inverse problems, and particularly for large-scale imaging. I know this is a concern for medical imaging. We often have to solve like 3D, even 4D, like dynamic MRI type imaging problems. So just a brief introduction. So the notation we're going to use for this is that the clean image will be denoted X, and we're going to focus on linear inverse problems for this presentation, which we denote with the system matrix A. Now with the inverse problems, we can represent this as sampling from a posterior. That's the P of X condition on the measurement Y. And diffusion models have been known to give pretty good results when solving inverse problems since they provide a strong prior P of X. And we've already seen many times in yesterday's presentations of how there's many different works on learning this prior P of X. And roughly speaking, the pipeline for using diffusion models to solve an inverse problem first consists of the diffusion process, which is this generative process where we start t equal to 1 is a pure noise, and then gradually in an iterative way we denoise the image and eventually obtaining a clean image, which is t equal to 0. Now this is just generating an image, but to solve an inverse problem we also need consistency with the measurement, that's y. So here we have an example of just a deblurring problem where we have this blurry image y, and I've made this kind of vague on purpose because there's a variety of different works on how to do this. But roughly speaking, you can feed this degraded image using some kind of conditioning mechanism or inverse guidance, such as a gradient method, to enforce that at each step your image is somewhat consistent with the measurement y. And then at the end, the hope is that we get a reconstruction which is both consistent with the measurement y as well as is clean looking. Okay, so there's like some limitations for this is that learning the prior P of X is very hard, and it's like the most important thing about solving the inverse problem well. For example, we need a lot of data as well as the training time being very long. And you can imagine the distribution of these images is pretty complicated usually. If we have like a 256 squared image, that's a lot of numbers we have to learn. So the networks involved usually have a lot of parameters too, which means that you have issues with memory as well as overfitting. And really the biggest problem is that we cannot directly use these kind of approaches either for a high resolution or 3D images directly, right? I mean, not only is it not possible to just fit that image into the memory, but you also do not have enough clean data. For like a 3D medical example, we do not have like hundreds of thousands of clean volumes of patient data. Okay? And that's the problem that we're going to tackle today. And I'm going to highlight these two approaches, where the first approach is to break an image into smaller patches, and then the second approach is to break a 3D volume into groups of slices. And we're going to see how we can put these together in a clever way to form an image prior. Okay, so like the first method is to use patches. So the first step is we have this clean CT image here, which is in 2D. We first zero pad the image to get a larger image here. So I've just given some dimensions here just for reference, but in general they can be more arbitrary. Now after zero padding, we can first select the random patch location, which I've denoted with this arrow here. And then this is going to give rise to a way of tiling the image using patches. So here we have this 4x4 grid where each square represents a square patch. And then there's also this outer boundary area, which is all zeros. So then we can represent the score function of the entire image, that's the log P of X, as the sum. So this sum is actually going to run over all its possible ways to select a random patch location, and we're going to take an average over them. And then inside we have the score of the boundary, which is this represented by the B. And we know this is all zeros, so it's not super important, but we just have to represent it anyway, as well as all of the scores of the individual square patches. Okay, so this is a way to represent like the score of the entire image as the sum of all the patches. We also have to add a positional encoding, which is telling the network where each patch came from. So for example, for CT images, we know that like the spine usually is toward the center in the lower part of the image. So we tell the network that the patch came from that area of the image. It can know that probably there's a spine there. And by doing a random patch location, we can actually eliminate the boundary artifacts. We know that there's like many previous works in the literature about using patches on images, but there's different ways to address these boundary artifacts that appear between the patches. By changing this random patch location, we can actually fix this issue. Now, this is an unconditional prior, so we're not even solving an inverse problem yet. So we can just look at what kind of generations we get unconditionally. Okay. So first off, the top is some examples of generations just using a traditional diffusion model. That is one that is trained on a whole image. Okay? And they look pretty reasonable, right? I mean, diffusion models are known to give pretty good results at image generation. Okay? So middle is what happens if we do not do any patch shifting, which is, in other words, if you just fix a patch location, you do not change it throughout the process, then we see that there's these very obvious boundary artifacts, okay? Because I mean, the network never sees the boundary, so it will not know how to piece them together in a coherent way. And the bottom is what happens if we actually use this patch shifting mechanism, right? And we can see that the boundary artifacts have been completely smoothed out, but not so much to blur the whole image. Okay? Yeah, so this is just an example of the unconditional prior, but now let's see how to actually solve inverse problems. Okay, so to recap, the training process actually is going to consist of extracting a random patch from an image, as well as the X and Y positional arrays. And this is two arrays that are the same size as the original patch, where each pixel has the X and Y positions, where they're normalized between -1 and +1. So since these three patches are all the same size, we can just concatenate them along the channel dimension, and then input that into a UNet, this traditional architecture for training diffusion models, as well as input a noise level. And all this is standard practice for training diffusion models. Okay. Now we use a denoising score matching process to learn a denoiser for the patches. Now for reconstruction time, we have this measurement here, which is in this case a sinogram for our CT reconstruction problem. We initialize with pure noise as is standard for diffusion models. And then for the process, we first randomly choose a patch location. So that's given by this upper left point, which gives rise to this way to break up an image into patches. So these 4 red patches I've drawn here. And then these 4 patches are separately input into the network, right? So this is a pretty crucial point because we're not ever going to input the whole image into the network, which is going to reduce the memory requirement a lot. And now that we've separately sort of denoised these 4 patches using our network, we can then just put them together naively to get this image here. And you might wonder, why wouldn't there be boundary artifacts between these boundaries that I've drawn here? And there probably will be artifacts in this iteration, but diffusion model has T iterations where T is like 1,000 usually. So the next iteration, when this, now we have now broken up an image in a different way, this boundary artifact will no longer be there. We will be able to eliminate it using the next iteration. Over the course of this many iterations, actually, there will not be any boundary artifacts. Eventually, we will get the clean image here. Yeah, so just some highlighting some of the salient points of the algorithm. The denoising process is actually almost identical to a traditional diffusion model. We just add noise to the image, X plus epsilon. We train the denoising network d theta, and then average over all our images in the data set. I want to also highlight one other point, which is that we have to randomly select these integers, I and j, which represent our patch location that I mentioned, which gives rise to the score function of an entire image. And then we use the sampling algorithm Langevin dynamics, which was covered a bit yesterday, which is essentially just gradient ascent of p of x to some degree with some random noise. And then we use the DPS method, which Webb covered extensively yesterday for data consistency. Okay, so just some quick results. We did some experiments on a variety of different linear inverse problems. For CT, I've listed the geometric properties down below here. But we're doing very sparse view CT, right? So with 20 and 8 views. I'm going to draw your attention to these 2 comparison methods down below here, which are patch averaging and patch stitching. So what I just mentioned is just one way of putting together patches in a way to reduce the boundary artifacts and form a prior for the image. But people in the literature have also come up with these 2 other ways to do this. And so we've compared against those as well, right? So notably, these 3 methods down below all train the network the same way. They all train patch-based networks that never see the whole image. But the difference is how we put them together. Okay. All right, and we see that our method does pretty well in all the inverse problems. Right? We've also compared with some plug-and-play methods, traditional methods, as well as the whole image diffusion method, which is just traditionally, once again, we're just learning diffusion model on the entire image. Okay? I also want to just point out one fact, which is that we trained our image or our models on only about 2,000 images for this experiment. If we had many hundreds of thousands of images, as is usually needed for training a diffusion model, it is likely the case that the whole image model will do as well as or even outperform patch-based models, which is not surprising. But in this limited data setting, the patches provides a way to augment the data, reduce overfitting, and that's one of the reasons why the image quality is better. Okay, so here's just a visualization. I've made this plot on Hounsfield units here. So mainly wanted to highlight that with whole image models, I've already mentioned this issue with overfitting to the data. There's some works in the literature that demonstrate if you only have like a couple thousand images, the diffusion model will tend to memorize the data, which means it will just spit out what is already in the training data set. And this will lead to these kind of artifacts that we see here. Right? Whereas these artifacts are much less apparent for our patch-based model. Okay. All right, just want to show one quick other study, which is that for the patch size, if we think about what happens if we use a very small patch, then it's harder to capture the dynamics of the image in longer range correlations as well, which is why we see lower performance quality for this smaller patch size, as well as if we go very large in the patch size to the most extreme case, that's when p equal to just the entire image, then we get the whole image model. And then for the same reasons I mentioned, we get lower image quality. Okay, so there's a sweet spot in the middle where we both capture enough image dynamics, as well as we don't overfit and memorize the data. And the data set size is another important point, which I've already briefly alluded to. But if we go even smaller than our experiments in the previous table, down to about 100 images, then we see that the patch-based model is actually much more robust to this small data set size. In particular, the PSNR only drops about 1 dB compared to our original experiment, whereas the whole image model drops even more. Okay. So even more issues with overfitting. All right, now I want to switch gears and go to 3D diffusion models, and this is the other work. And for 3D, it's an even harder problem because the volumes usually have size about 256 cubed, or maybe the third dimension is even larger for CT reconstruction. And previously in the literature, some approaches that people have done is do this slice-by-slice training method, which is we break up a 3D volume into 2D slices, as so. We separately train diffusion models on each of the slices. When I say separately, I mean using the same network, but the images are fed in to the network separately, and the denoising is done completely separately. And then the denoised images, since the network never sees adjacent slices, we have to use a regularization method to enforce that they're actually smooth. And what people have done is use this total variation regularizer. Okay? But we've already seen that in the past decade or so, data-driven methods have outperformed these handcrafted regularization methods. So there's no reason to believe that this TV regularizer should be the best method. In particular, we propose a data-driven method to enforce the smoothness between slices and learn more global information between far away slices. Okay? And that's going to be our diffusion blend method, which I will cover now. Okay, so first if we look at the figure on the left, for simplicity, I'm just going to assume that our volume has 9 slices, although in practice it might have a lot more, such as like 500. But the point is that we first take the top 3 slices, which I've shaded in the same color, to show that we're inputting these 3 into the network at the same time. So we're actually learning the distribution, the joint distribution of these 3 slices at the same time. And we can concatenate them along the channel dimension, which makes it still a 2D volume, or a 2D image, right? So we don't need a 3D unit to learn this, we still use a 2D unit. And then same thing with the 3 green slices, we train a network to learn the distribution of those 3 green ones at the same time, as well as the 3 purple ones, okay? And so the problem with just doing this though is that, once again, the network never sees the bordering information between the bottom orange and the top green slices, which will once again lead to discontinuities in these artifacts. Okay, same with the top purple slice and the bottom green. So this is why we also have these other ways of breaking up a volume into slices in a discontinuous fashion. Now here I've highlighted the orange slices that are not together, but when we process them using a network and train the network, we still concatenate them together as if they were together in the same volume, and then learn the distribution that way. And then the other detail is since the slices were actually not together in the volume, we input this positional encoding number, which happens to be 3 here, to actually tell the network, like, yeah, these slices, they did not come all the way together. They're actually farther apart, right? Whereas here, we're just inputting the number 1 to show that they are together. Okay? And here's another way of breaking up this volume into slices. You can imagine there's many different ways of partitioning this volume slice-wise, 3 at a time. Each time we have a different positional encoding number to tell the network the slices did not come from the same spot, or maybe they did. Okay? And then of course we're solving inverse problems, so we have to also input the sinogram. And this is done with another similar method as DPS, but this is another off-the-shelf inverse problem solving method, which I will not go into here. Okay. For more clarity, like I mentioned, so each method of breaking up a volume actually corresponds to a partition of each of the slices. So for example, on the left, we have this partition here, where like 1, 2, 3 are all together, 4, 5, 6 are together, and so on. And essentially, we're just taking the score of the entire volume to be the average of the scores formed of each of the partitions. So this inner sum here, that's we're summing over each of the partitions, or each of the sets in the partition. And the outer sum corresponds to taking an average over each such partition. Okay? And you can maybe already start to see the similarity from this method versus the patch-based method, right? It's like in both cases, we're taking like an average over some way of breaking up an image into smaller parts. Yeah, the other detail here is that there's a reason why we use 3 slices as opposed to some like other number, right? Now, intuitively, if we use like too many slices, we run into the same problem with before, which is memory issues. We have to fit a large volume into the network. But with 3 in particular, we can sort of pretend that the 3 channels of the image are RGB channels of a colored image, which means that we can fine-tune our network from a pre-trained checkpoint, in particular from ImageNet, because the ImageNet is a very large data set, and the people have trained these networks very well on this data set. So by fine-tuning, what I mean is we initialize our checkpoint on this checkpoint that's been trained on ImageNet already, and then we just train from there. Okay? And empirically, people have done more systematic studies on this and show that by doing this fine-tuning strategy, you can reduce the data requirement as well as the training time. Because I mean, the data requirements that I mentioned in the previous slides are still there. We don't really have like hundreds of thousands of these images available, but by fine-tuning like this, it's possible to train networks on much smaller data set sizes. Okay, yeah, just a brief highlight of this reconstruction algorithm. The main point is that at each iteration step, we have to select a partition, which I've already highlighted a couple of different ways to do this. Now, in particular, just using some terminology, which is that if we go back here, these partitions are known as adjacent partitions because the slices are all together, whereas these are called cross partitions since the slices come from farther away. Okay? This also helps us learn more global information across the volume. We also have to compute this positional encoding, like I mentioned, to tell the network like how far apart did the slices come from, right? Okay, so some 3D CT results. We have both sparse view CT. This is very sparse view with only 8 views down to 4 views, as well as in the paper we have some limited angle CT experiments. And we compared with mostly a variety of different diffusion model-based methods. So DDS is one method that I've mentioned previously, where they use the total variation regularizer between slices in the D direction. And this is just to enforce the smoothness. For our approach, like I mentioned, we actually don't need this regularizer at all, because we already have this mechanism of enforcing smoothness. Okay, so we see that our method is just significantly better than these previous methods due to this ability to learn this joint information between multiple different slices. Wait, here are some results for only using 4 views. This is a very, very sparse because, I mean, in the clinic, people usually have to use hundreds of views for CT reconstruction. We're actually able to obtain pretty good results with only 4 views. Now, of course, there are some assumptions here, such as the inverse crime and no noise. But since we only have 4 views, we can afford to have very high intensity for each of the views. So it's a reasonable assumption for now to not have much scatter. Yeah, so we can look at the zoomed in region here, where the ground truth is on the far right. It's pretty consistent, whereas it's much more blurry from these previous methods, partially due to the fact that we have this regularization, right? Whenever we have this regularizer, we can probably expect some degree of blurring. Okay, and just to compare the wall time, yeah, this is a pretty slow process. Even our method, it's a pretty big improvement over some of the previous methods, but it's still pretty slow, just because diffusion models in general, they're an iterative process which requires a lot of iterations, but at least it's a big improvement over some of the previous methods. as well as we did an ablation study on whether or not it's useful to do this process that I highlighted of choosing different partitions, right? Both using adjacency partitions as well as these cross partitions, which use jump slices. And we do notice a small improvement, but it's definitely there when using these different ways of partitions. Okay, now I want to just briefly go over a connection between the two methods that I've already went over. So as a recap, with patches, we're randomly choosing a patch location, which gives rise to a method of breaking up an image into these different patches, whereas the score function is represented in this way. And with diffusion blend, the work I just presented, each different partition of the volume gives rise to a way of representing the score function. Now, in both cases, the score functions actually take this format. S of x is an average of many different score functions. Okay. So for example, here we have an average over each of the random patch locations, and here is an average over each of the partitions. There's also a connection here to ordered subsets, which have been an idea in medical imaging reconstruction. But there's this very important theorem which is sort of similar to stochastic gradient descent, which is that if we're sampling with Langevin dynamics using the score function, instead of using the whole average, we can simply use randomly chosen SI of x at each iteration. And then making some assumptions, actually the sampling algorithm will lead to an image which is the same distribution as if we were to just use the entire S of x. Okay? And this is very similar to SGD because in SGD, instead of using the entire data set, which is very large, we can just simply choose one random data point to perform our gradient descent. But in my view, this is a more surprising result than SGD because in SGD, our goal is to eventually reach just one singular point, which is like the global minimum or a local minimum. Here, our goal is much harder. Our goal is to reach a distribution of images, which is a random process. And we're adding this additional amount of randomness into this process, which is this randomly chosen SI of x. And we've shown that actually that additional randomness does not, in some sense, cause the final distribution to be wider or more random. Actually, we reach the same exact distribution at the end, even though there's this additional randomness component. And of course, this is a very important theorem because it speeds up the algorithm significantly. For example, for patches, instead of just having to average over every single patch location, we can just simply choose one of them at each iteration. And for diffusion blend, instead of averaging over all the many, many different partitions, we simply choose one such partition at each iteration, and this will allow us to converge to the same distribution. Okay. Now, of course, there is a small caveat, which is that we didn't really incorporate the data fidelity term into this theorem. Actually, this is an ongoing work in research, which is how to sample from the posterior exactly. There's a lot of methods such as the DPS, which approximately sample from the posterior, but they've provably been shown not to sample from the posterior exactly. Okay. But at any rate, if we were just to do unconditional generation, this theorem gives us assurance that this sort of ad hoc process of randomly choosing a way is actually theoretically sound. And there are, just as another final side note, there are some previous works in the literature which implicitly use this theorem, but they do not state the theorem, they just sort of assume it works. Okay? And I'm happy to chat offline more on how those works and the connection between them. Okay, so with that, I think that should be the end of this presentation. Thanks for, maybe just one final slide of future work real quick. I think that really the main future work that we've been targeting is that distribution shift problems, which is problems where we train a network on one data set and then test on a different data set. And in medical imaging, we can see this is a pretty important problem because oftentimes we might not have enough patient data to train a network on that kind of data set. So we will first have to train a data set or network on some other data set and then adjust it on the fly for a new data set. And this is the work that we've submitted that's on arXiv currently. You can check out, and we're still working on this. Okay, so with that, thanks for your attention.
Okay, talk's open for questions. Questions or, okay.
Thanks for a very interesting talk. I'm wondering, when you simulate the sparse view projections, do you add any projection noise?
Yeah, so we don't add any projection noise to our simulations for these experiments here, so no noise here. Since the number of views is very low, we can afford to have a lot of intensity for each of the views, so it's reasonable to assume that there's very minimal scatter. Although in the paper we do have an ablation study to show that our method still performs pretty reasonably even in the presence of scatter noise.
Okay, so follow-up question. The sparse CT is kind of low-dose scanning. So another potential setup is we do a 4-view scan, but we lower exposure for each view, right? So do you think your diffusion blend methods can also apply to that low exposure scanning?
Yeah, so definitely a similar method can apply, although if the noise is very high, then since the noise will become more Poisson rather than Gaussian, in that case, there may be some adjustments that have to be made, but certainly the same principle would apply.
Okay, thank you.
So I have an online question from Matthew Holbrook. Great presentation. My question is on positional encoding for the patch method. For image generation, positional encoding seems necessary to create a coherent image. But for inverse problems, is the encoding necessary since the measurements already provide coherent positional information? And then was reconstruction tested with and without positional encoding?
Yeah. So we use positional encoding in all of the experiments for both generation as well as inverse problems. It turns out that we do have this ablation study in the paper of what happens if we try to solve an inverse problem without using positional encoding, and the results are quite bad. I think maybe one of the reasons why is because we think about all the different patches that came from an image. There's all sorts of different patches, and it's really a huge mixture of Gaussians. I say Gaussians, but it's not really that, but you can imagine it as like a mixture of a massive number of Gaussians. When we add the positional encoding, it's sort of like informing the network of which Gaussian did our patch come from, and it really helps the network narrow down what is the distribution we're trying to learn. I think there's, sorry, what was the second question?
It was, did you test with and without position?
Right,
So I think you got that. Yeah, Beijing.
Thanks, Jason. Very pretty presentation. So I have a question about that. Like you are in your 3D work, you use like you put all the Z dimension as the channel. So it's actually average of all the channel in the score. So can it well represent the 3D structure? Like it's not equivalent for your XY plane and Z dimension, right?
So just maybe just to repeat your question, is it that whether or not this score function is actually representative of the 3D volume? Is that basically the question?
No, my question is you put the Z dimension in the channel, right?
Yes.
So actually your convolution kernel is applied in your XY plane, so it's not equivalent for your XY plane and Z dimension. So can it well learn the 3D structure in the Z direction?
Right. Yeah, so I mean, definitely that is a concern, right? And that since we're only using a 2D unit here, we're not using a 3D unit, there might be some dynamics that is lost between the channels. Now, of course, in the ideal case, we would like to use 3D units as well as more than just 3 slices, right? To learn longer range correlations of the slices. But yeah, the problem is that we will run into sort of memory issues if we try to use these kind of 3D units. There's also one other work that has been proposed, which uses a pair of networks, where one is trained in the axial dimension, the other is trained in the coronal dimension, and we alternate between these 2 different updates. But that method is pretty slow, and also it restricts ourselves to using only cubic volumes. Whereas in practice, a CT volume can often have a different number of axial slices. Imagine in the body, it can often be like very, very long. In that case, this approach is more flexible.
Thanks. And I have a following question. So in your theorem part, do you need to assume that all the slices has to be the independent, or you don't need this assumption?
Yeah, so in this theory, actually, so this is actually a more general theorem than even like the 3D case or even the patches. It's basically just saying that in general, if we have some score function represented in this way, then it is fine to just take one of the SIX iteration for each of the iterations. So this can be like some very crazy thing you imagine. Maybe there's like some kind of sort of mixture model, right? If there's some image and we have different competing ways of how we can represent the score function, basically what it's just saying is that we just choose one of the different ways of doing it. So there's no assumption made on the dependence.
Thanks.
So maybe one more quick question from online. How valid, this is an anonymous question, but how valid is the assumption that the score can be decomposed into this sum?
Yeah, so that's a difficult question. I think okay, so if we go to there's sort of these two different works, and if we go to patches, that's all the way down back here. So this is the one such decomposition. It's certainly not perfect because, I mean, the score function doesn't really capture long-range correlations very well. So the positional encoding is able to tell the network like where each patch came from, but it isn't able to say like, if I have this particular aspect of an image in the upper left-hand corner, then I should have this other aspect in the lower right-hand corner. So there's no way for the network to know that. So it's definitely not a perfect representation. And just similar issue with the 3D volume case. But this is why, for image generation, these methods are maybe not ideal because there's no way to capture this long-range correlation, at least not without some adjustments. Okay? But certainly for inverse problem, like has been highlighted, since the measurement already provides some semblance of what the image should globally look like, it's very useful.
Let's thank Jason once more time.